So this will be a very different talk than the last one we heard. So like a lot of philosophers, I'm interested in very general questions. And this is a question that I've pursued in very different ways. What are the nature, scope, and limits of knowledge in physics? And other philosophers of science have looked at other fields, of course. I've just by chance ended up, and by interest, working primarily on physics. And really, I've been looking a lot at trying to understand what's going on in physics in order to answer these sorts of epistemological questions. I've often pursued historical case studies, looking at the detailed development. Looking at the detailed development of particular fields as a way to try to address this question. But today I want to talk about a different question, focusing on a type of sciences or a kind of approach to scientific projects that I'll loosely call historical sciences. And so this actually, I should credit a former PhD student of mine, Craig Fox, who worked on this for a thesis a few years ago. So it was really working with him that got me interested in these questions. And also, of course, it's relevant to cosmology, which is something I've thought a lot about. And it turns out that there's a small group of people within philosophy of science who've been looking at this question as well. So I think a shared theme of discussions of historical sciences is that, and this is not surprising, that a lot of the reasoning in historical sciences is reconstructing history based on traces that we have in the present. And the question is, how much can we do with that? So I think there was, for a while, a sort of crude assumption that the historical sciences were worse off compared to experimental sciences. And that you'd face a kind of underdetermination threat in historical sciences. There are different ways of expressing this worry. One is just that you would have a sort of decay or loss of information over time so that the traces of past events will be harder to access later. And also just the obvious fact that we don't have the ability to manipulate historical systems in the way that we often are able to manipulate experimental systems. So there's a variety of people who've I've classified as pessimists. Sober's more complicated. He's optimistic about some things and has some more pessimistic arguments as well. Derek Turner had the misfortune of doing what philosophers often do, which is announce that certain things will be impossible. So he, as a side note in a paper, said, well, there are some things we'll never know about the past, such as the color of dinosaurs. Like a lot of philosophical pronouncements of that sort, that was like a prelude to conquest by science. So a few years later, paleontologists gathered evidence that seems to give them good grounds for establishing what the color of dinosaurs are. So I think these are real concerns, and I think one of the overall questions I often ask in trying to address the big question is, what are the evidential challenges that a field faces, and how have scientists overcome those challenges, and to what extent have they done so? The more recent literature on historical sciences, and here Adrian Curry's book is a good example. You can see just in the subtitle of the book, it's an optimist guide to the historical sciences, and so he's really defending the claim that historical sciences have been able to establish results with as much certainty as we have in other areas of science. And some of this work has focused on case studies of specific examples of historical sciences that seem to have delivered really firm results and knowledge of the past. There's one kind of argument that, so Carol Cleland in particular in a 2001 paper argued that we can address the pessimist worry by appealing to an asymmetry of overdetermination, that the effects overdetermine causes. And so there's a way of thinking about this that she's borrowing from the philosopher David Lewis and his analysis of the asymmetry of causation. And I think, although I'm much more on the optimist side, I find that way of framing the discussion to be a bit limiting. And partly there's things that I'll leave off stage, just it's partly criticisms of Lewis's analysis of counterfactual asymmetry. But what I'd like to do today is to suggest a different way of framing the discussion that's based on some of the causation and especially the interventionist approach to causation that I've been dipping into recently. So this was an invitation that came at a good time because I've just started looking at this, and so it's great to have benefited from the talks yesterday, and you'll see that there's a lot of common themes. So the way I think that it's possible to pose the question slightly differently is to say, what does the world have to be like to enable reliable reconstructions of the deep past, insofar as we have been able to succeed in giving those? And I'm going to focus just on two aspects of this question here. So there's a phrase I think is originally Jim Woodward's, but it's in the title of a paper by Naftali and Jim and Porter Williams, a really recent paper, that says, the question is, what's the worldly infrastructure? So what has to be present in the world to underwrite our ability to make causal inferences. And so I think there's some very similar features that are important for understanding causal inferences in the deep past. And so I should say also, I think it's important that these are causal inferences because I think the scientists who are investigating the deep past are not just interested in establishing what happened, they're also interested in establishing causal accounts of what happened. So I think it is crucial that it's a causal inference and not just a reconstruction effort. And the other point I'll make, I think the methodology of trace-based reasoning and reconstructions based on traces is certainly substantially correct, but I think there's actually a stronger notion. There are some cases which I'll call time capsules, and it might be more a difference of degree than of kind, but there are some kinds of systems that allow us to make astonishingly good inferences about past states. And so I'm going to argue that the feature of the world that allows for those kinds of time capsules is a kind of decoupling that's been mentioned in a few earlier talks already. So those are the two things I'm going to focus on as the features that I think the world has to have in order to underwrite reconstructions of the deep past. So let me start by I'll first talk about the relevant notion of independence before going back to decoupling and traces, and then I'll very briefly comment on early universe cosmology. So I'm going to use an example here briefly to illustrate the importance of a notion of independence of the initial conditions. So this goes back to the 19th century when Ludwig Boltzmann derived what he called the H theorem. So the image across the top is meant to be something like an ideal gas interacting where it's just pairwise interactions between the gas molecules bouncing off of each other. And this is meant to be a time series where you can see and if you look at the red, you can see that the red dots move in such a way that you could imagine that they've interacted with the nearby particles and have bounced off of them. Now, the striking thing that Boltzmann derived is that he argued that there's an evolution towards an equilibrium state, namely a particular distribution of velocities in the gas called the Maxwellian velocity distribution. But, as various people soon pointed out, that was incredibly puzzling because the dynamics describing these collisions, the pairwise collisions between the molecules, were completely time reversal invariant. So how could you get a monotonic evolution towards equilibrium when you have time reversal invariant dynamics? And the source of the asymmetry was an assumption that might have seemed innocent, which he called the Stoßzahlansatz, which we usually call molecular chaos, which is that the interacting particles, before they collide, their states, their velocities, and positions are independent of one another. They're not correlated. But of course, that's a time asymmetric assumption. If you have the two particles collide, afterwards their velocities and positions will be correlated with one another. And so by initially setting those correlations aside, you're introducing a subtle sort of time asymmetric initial condition. So, and you can think about how you could set up an anti-thermodynamic evolution, namely an ideal gas that doesn't go towards equilibrium, doesn't go towards the Maxwellian velocity distribution. So this is the way to set it up. Consider any system that evolves towards equilibrium. Now imagine that you can reverse all of the velocities of the particles, and the microstate that you've defined in this way, under the dynamics, there's an allowed evolution that goes exactly the opposite of the evolution that just got you into the state. And so that final microstate will then evolve away from equilibrium. But there's some really surprising things about this, right? The first is that what you're doing is taking all the correlations that exist in that final state and you're using the dynamics to sort of unwind those to take you back towards the initial state. And so it's an anti-thermodynamic evolution in the sense that this is not the kind of thing we see everyday gases doing. It's against all of the features we see, the evolution towards equilibrium. But the thing I want to focus on is just that there are really two features of this anti-thermodynamic evolution that we can think of in terms of the independence of the state. So first of all, when I've defined this state this way, I've defined a state that has a huge number of complicated correlations between the states of the particles. Right? That's how I've introduced it. And that's essential to have those correlations present in order to be able to determine that dynamical trajectory. The There's a second point, which is a little more subtle. It's also the case that the reverse state is dependent on the dynamics that I've used to describe the evolution of the gas. If I had a slightly different dynamics, that abnormal state, even though it's got all the correlations, wouldn't evolve antithermodynamically, right? So it's both the state has in the specification of the particles, they're all very delicately dependent on each other, and exactly what state it is that leads to the antithermodynamic evolution depends on the knowledge of the dynamics of that system as well. And I should say I have various references here. Very little of what I'm saying now is original at all. It's just setting up a point, or maybe nothing I'm saying at this point is original. Now, I think there's a number of similar kinds of assumptions about independence that arise in physics. So the first point is we can just generalize what Boltzmann was talking about, and it arises in other cases where physicists in statistical mechanics derive time asymmetric macroscopic dynamics using coarse graining and so on. I'm not going to go into the details of that. But a lot of these technical practices involve something much like what we saw in Boltzmann H theorem, namely throwing away correlations between subsystems in order to derive an asymmetric evolution. You can also see this in an assumption of no source-free radiation. So this is often illustrated using the example of a stone thrown into a pond. When we throw a stone in a pond, we see the waves ripple out. We very rarely see waves converge and cause a stone to be thrown out of the pond. That kind of evolution would require the same sort of coherent evolution from this state in order to have the kind of time reversal of what we usually would expect to see. And so there's another condition that you can impose that will rule out exactly that kind of case. And finally, I mean, we could go on. There's a lot of different cases that illustrate this point. Here's a more subtle one. It's actually there's a recent paper by Williams, Miller, and Doherty that analyzes something that Weinberg introduced as an axiom of QFT, the cluster decomposition principle, as he called it. So imagine you have clusters of fields interacting with one another, and then you take those to be further and further away. And the claim is that the vacuum expectation values, or the S matrix elements that you would use to calculate things in particle accelerators, that those become independent as you move those far away. So again, it's a way of saying that the probability distribution factorizes is a precise way of making this independence claim. And again, I think this is the kind of thing that you will find in a lot of different aspects of physics, independence assumptions of this sort. So I think we can see the interventionist approach to causation, as Woodward formulates it, as highlighting two very similar features to what I've just introduced in terms of the physics. So these are more general statements of the same kind of independence that I've seen, that I've been highlighting as well motivated physically. So the first is very close to the causal Markov condition that we saw in Thomas's talk yesterday. I think this is actually slightly weaker logically. But if we have a bunch of random variables, if none are causes of other variables and none share a common cause, then they should be statistically independent. So that's like the first claim I was saying. And the second, I don't really like the name, but I guess it's good enough, value relationship independence. This is related to the idea that the way that the initial variables are specified should be independent of the law or the causal generalization that's relevant to them. So these are exactly the two features we saw earlier in the case of the Boltzmann H theorem. So I think let me just pause for a moment and emphasize here. So the point is, I think these aspects of the interventionist program are actually good ways of characterizing independence postulates that play an essential role in physics as well. And so I see these as sort of a generalization from plausible physical principles that seem to play an important role in a variety of aspects of physics. Now, I think a natural response that you might have had when I said I was going to use an interventionist approach to causation and thinking about the history of the deep past is to say, interventions, why are you talking about interventions, right? So, and this is just, again, we saw this yesterday in several talks, a definition of cause from an interventionist program requires that, that it's, in effect, you're able to pick out and directly intervene on a cause that then has the intended effect. And so the question here would be, is it possible to control a variable y, and only that variable, by acting on its cause, right? So can you locate a sort of surgical intervention in that kind of way? Now, the reason why this might seem implausible is something we try to apply to the deep past is what could we mean by possible here, right? So if you're doing an experimental science, you could try to do these directly to assess the possibility, because you could determine whether your causal graph is appropriately modeling the data you're looking at by trying the interventions and seeing what happens. So but there's a basic question here about how do we assess possibility. And I think actually, so this goes back to Woodward's book from several years ago now. I don't think we need to think possible as just experimental manipulation. There's a much broader notion of possibility here. And so as Woodward says, he doesn't even think it has to mean physically possible. He has a little bit further discussion here about a strong sense of physical possibility and so on. But really the question is, can you define an intervention? Can you actually specify an intervention that would have the features that we noted before? And I think in a lot of cases, we can actually think of defining interventions in a much looser way, namely that we can think of, obviously an experimental context, but we can think of natural experiments where we think of the environment as having an impact on the system where it will influence a particular variable. And so natural experiments allow you to see that you can have, if nature cooperates, you can see the variation in that variable as a result of the way the system interacts with the environment. So you have, in effect, implemented that manipulation by looking at these separate systems. And I think we also can assess these questions of possibility in some cases by doing simulations, where we can explore the possibility space and see what's possible in terms of varying different variables. So it's not really something that is tied to human capabilities in this definition of causation. But I do think it's really important to ask, so all of these assessments do involve some kind of modal commitments. So what's the way that the system interacts with the environment? How do we think about possibility? How's that enshrined in our simulations? So I think we do want to say that we can only use this if our modal assessments are at least have clear truth conditions so that we can determine whether a particular intervention is possible. Now let me say, if we think of our anti-thermodynamic evolution, and we imagine the gas now evolving away from equilibrium, and let's say we tried to intervene on that system in some way, right, so that we would modify its course of evolution. Here I think, when we start to think about this, we can see how hard it is to imagine what an intervention would look like in that case. That's because anything we might try to do would disrupt the carefully coordinated evolution that's leading it away from equilibrium. And so it seems like any intervention is going to, rather than changing, let's say we wanted to change something about the final state, any intervention is going to change everything about the system, right? And so this is a point made that, by Adam Elga, and then Porter Williams has another recent discussion of this. So it's hard to see how you could intervene in a system that had that kind of evolution. So that's a case where I'd say if you're trying to intervene in a world that had a failure of independence, then it seems I have no understanding of what interventions would mean in that context. But I think in other contexts, we can say that we have an understanding of the modal assessment necessary to make these sorts of assessments. So I think we can, for example, going to the second point here, we can give a modal assessment of system-environment interactions, sources of exogenous variation. I think that's what people in historical sciences are often doing and have clear grounds for doing. As we'll come back to right at the end, I think it does get more tricky if we're talking about global properties of systems or global states or closed systems. And so the other thing, as I just emphasized before, I think the interventionist assumption of independence, the feature that I think is really interesting is that it depends not just on the laws, but it also depends on features of the initial state. The initial state is uncorrelated in an appropriate sense. So that's a brief summary of why I think the interventionist approach brings out some features of causal inference that we can helpfully apply to historical sciences. And I want to now shift to really briefly discuss decoupling and traces. So inferring causes from traces, this is the standard kind of picture that Thomas mentioned before as well, that we see all kinds of cases where we say there's an event, such as a baseball going through the window. You have a lot of evidence, the glass shards on the floor, the baseball, your child's sheepish look, or if it was one of my daughters, you'd just see them running out of the door to avoid what was coming next. But the traces then overdetermine the cause. That's the sort of line that Carol Cleland gives, and I think there's something that's right about it. But I think there's something that is missing in these accounts, which I think is actually really essential for at least the historical sciences that I've looked at, which is that I think there are cases that are quite a bit more powerful than just inference from traces. So Dave gave us a beautiful discussion of the CMB yesterday, so I deleted a bunch of slides. And the really crucial point that I want to emphasize is that after about 380,000 years after the Big Bang, the photons decouple, and they free stream essentially to our satellites that are observing them, or our TVs if you have an old TV. And through that evolution, the photons themselves, the average properties for the whole sky, there's really no dynamical process that is feasible that would modify the average temperature of the CMB, other than the fact that due to cosmological expansion, the temperature is changing with the scale factor. So if you ask, what is the mapping from the current observations of the CMB back to the early universe, it's really a direct mapping. So there are local variations, which are quite important, but you have a really direct mapping back to the early state of the universe. And so I think this seems to me stronger than a trace. And it's actually one thing that Dave also emphasized, but I think is worth saying once more. The CMB has driven cosmology for the last 50 years. So it's enabled precision cosmology in a way that other observations are now catching up to, but the level of precision that's available in observations of the CMB and the fact that we've kept coming back for more, there's more and more features of the CMB that have been revealing further details about the early universe that are very rich and important in constraining and understanding cosmological theories. So I think it's a bit stronger than just a trace. And so this is a group in 1957 at MIT who are confident that this time capsule that they're installing, I don't know where it is on campus, would be dug up in 2957, so they expect it to last for a millennia, so that's a good optimistic take. And I think that a lot of systems that people use in historical sciences are time capsules in roughly the sense of this sort of everyday time capsule. Namely, it's a quasi-isolated system that evolves according to its own dynamics in some sense. Like the CMB, there's an autonomous dynamics that governs the temperature. And it's quasi-isolated in the sense that there are very few dynamical interactions that will disturb the state of the time capsule. Obviously, this is defeasible, like it's something that you can have failures of that sort of isolation. But there are a lot of cases where the time capsules also give you further information, such as an internal clock that allows you to not just say, infer what the state of a system was earlier, but infer something about the time elapsed since it decoupled from the environment. And so this is actually a really rich source of information. And I have one example that is something that you might not have heard of before. So isotopic ratios are a good time capsule because there's very few things that change the isotopic ratios for radioactive elements. And so this is a mine in Gabon that in the early 70s, people discovered something quite unusual, and this was the Cold War era. The amount of uranium-235 compared to uranium-238 was wrong. And so they thought maybe there was some, maybe the Soviets had been doing something, maybe there's some kind of nuclear activity taking place. And it turns out there was nuclear activity, but it was actually naturally occurring nuclear reactors. So they, because of the low uranium-235 abundances, they did some reconstructions. And so this is a map that shows, and the black spots are where naturally occurring fission reactors took place about 1.7 billion years ago. And so what this illustrates is that there's a time capsule, the isotopic ratios are so secure that you're able to discover like what could possibly have changed those isotopic ratios. It's essentially only a fission reaction. And then they're able to reconstruct how could a fission reaction have taken place. It has to do with the groundwater. 1.7 billion years ago, there was more U-235 present. And then they could confirm that by looking at other kind of decay products of the interaction. And they could see also from the shape of the rock that it had been heated up quite significantly. So that's just an example of how the departure from this quasi-isolate dynamics is also incredibly revealing. Now, I've used examples from physics just because that's what I know, but I would expect that there are similar kinds of systems in biology and evolutionary biology where you can think of them as something more like a time capsule that gives you a very secure way of inferring earlier states of the system of interest. Okay, so what does the world have to be like to enable reconstructions of the deep past? Well, I focus first on worldly infrastructure. Now in terms of traces and time capsules, really, this is very similar to a theme that has come up in a few of the talks before, that what is important here is a kind of dynamical decoupling of systems from their environment so that they evolve independently and they can be treated as isolated systems. And that's something we've seen in other contexts in physics where people have been using effective field theories very well, where you have a kind of scale separation that allows you to treat these as separable. Now, obviously, this is going to be, I don't know that I can say much more generally about this. It's going to be very background theory dependent, being able to find a time capsule, figuring out how to use it. But I think our world does provide us with some of these time capsules and very persistent and revealing traces. Okay, so the very last brief comment on early universe cosmology. So I mentioned before, I think that there are some issues regarding cosmology, but I first want to say, I think this is a very limited part of cosmology that poses particular problems. So I think in a lot of cases in cosmology, we actually can try to make the modal assessment of whether something is a possible intervention by the same ways that we do in other contexts. So either through natural experiments, looking at a large sample of similar systems and seeing how some features vary across the different elements of that ensemble, or exploring possibility spaces through simulations where we have a large confidence in the theories that we're using to construct those simulations. So I think for a lot of questions in cosmology, we can answer these interventionist questions perfectly well. I think in some cases, though, and in particular in the early universe, this is more of an n=1 problem, as Dave emphasized last time, because we don't have any other realizations, and then we face the difficulty of drawing a contrast between law-like and contingent features. And furthermore, the theory that's developed to render an observed history plausible, to make it the case that what we see is to be expected, given our understanding of the dynamics, is also really only tested through those same observations and the ability to reconstruct history. So there's a kind of worry about a circularity there that I think is really hard to get around. So I think in that case, it's not clear that the interventionist approach helps in addressing that problem, just because we face the problem of not really understanding modalities as clearly as we do in other contexts. Okay, so just to summarize then, what does the world have to be like to enable reliable reconstructions? So I've argued that the kinds of assumptions that are needed to be in place for a causal, interventionist causal analysis also have to be in place here, that we need independence assumptions, and then also to understand the modal status of interventions, and also that I think there's more interesting kinds of traces, which I've called time capsules, that really do provide a lot of information. And what seems to be the general feature that allows for those to exist is a decoupling of systems that makes it possible for those to be treated as effectively isolated. So thank you very much.
For keeping the time. Questions? Eduardo?
Thank you, Chris. Very, very interesting talk. I just want to hear your thoughts. You were telling us how you feel comfortable moving some data in cosmology from maybe traces to something that you would call evidence or observation. And I wonder, why do we need Aren't we, I mean, I was just pulling up an essay that most of you probably know because it's by Carl Sagan on the burden of skepticism that I give to the students all the time, right? Why do we need to do that unless what we're trying to do is to move from just taking the results face value to making decisions that are contingent on whether we're going to consider it a trace or a confirmed fact? And it was making me think about how I would like science or society to operate with the same kind of data if you are discussing further uncertainty in our monkeys, or you have a human being in a court of law who may go to jail for my assessments of paternity. It could be the same numbers, the same data, but we may still decide to call one not enough to make onto moving the decision, and the other one I can live with making. I mean, I allow myself to call this a fact if I'm discussing our monkeys in a workshop at Yale, but I may decide I'm going to keep calling it a trace because I do not want to pass judgment on somebody who may or may not be the father of this young. So I think, again, it takes us going back and forth between the actual results and our assumption that we're going to use that for something else.
Right. No, I think this is a general feature that epistemic standards that are appropriate to different contexts shift, right? So I think, and I think cosmology, there aren't as many decision contexts where it really matters if you've got the right value of the Hubble constant, right? So I think there's different ways of asking the decision question, though, which I think if you're going to take something as giving you insight into the causal structure of how the universe evolved, I think that gives you a much richer sense of the further consequences of that. And so this is a slightly different question. You're asking more like, how should we classify something as a trace, or how confident should we be in thinking of it as a time capsule? There's also then, if you use it in a certain way, you might get a better picture of like, here's the causal structure, and then that might have further implications for other aspects of cosmological modeling, right? So I think in cosmology, just because it's intrinsically incredibly valuable field, but not something that has like direct extrinsic impact on day-to-day decisions for the most part, I think that's going to be the impact. It's more on the implications for other aspects of cosmological modeling. And then, yeah, I think your degree of confidence can shift. Like if it's something that you think is an essential feature of your modeling and you're going to build like 20 years worth of research on this, you'd probably have I think a different way this comes up is like motivating large-scale, very expensive telescopes. You want to have a lot of confidence that what you're looking for is really something that's going to be very decisive in answering the question you're interested in. And so you might then have a very careful analysis of like, how certain are we about this as a source of evidence?
So when we want to make decisions about public money investment, right, for example. Yeah, Alex?
Thanks. I wanted to just ask a bit more about the focus on the deep past as opposed to recent past, because it seemed like, this question of kind of what's the scope and limits of our knowledge about the deep past, you could also ask it about the recent past, and you were saying that for current or recent things, we can like perform experiments in a way that we can't directly perform experiments about the deep past. But on the other hand, it is still true that in order to be able to trust our memories of the recent past, we were relying on assumptions about there aren't a lot of anti-thermodynamic things happening. So I was wondering, like, the conditions you listed, would you also think them to be basically necessary for knowledge of the recent past? And if so, then how do you see the focus on the deep past as, what's the importance of that focus as opposed to just focus on the past in general?
No, so there's a lot of the story that I think would be roughly the same for the recent past. So you have to have an account of memory, you have to have an account of how it is that you form records or take certain things as records. And I think that doesn't really discriminate between the deep past and recent past. So a lot of what I say, I think, just does carry over. But I think partly it's within the context of the recent discussions of the historical sciences that people are stating these kinds of pessimism that do depend on the amount of time lapse. So I think for some of the skeptics, even if you imagine that, if my daughter broke the window yesterday, I could find the traces. If that's the way you think of the evidence is working, and you think that those traces decay over time, then you have a reason for thinking that the account of the recent past just won't extend that far. And part of what I'm arguing is actually if you have something like a time capsule, that actually can be stable over 13.8 billion years, right? So I think that some of what I'm saying is that there are some systems that allow you to extend much more straightforwardly into the deep past. And I think that just hasn't been fully recognized in this literature.
The reliability of the evidence, right, basically, can be quite different. So in the interest of not keeping everyone away from lunch too long, let's thank Chris and move on to our final pre-lunch talk.